Yeah, yeah, sure, sure. Yes, in part, yes. He doesn't have a PhD because in the Italian system there was no PhD at the very beginning. So he was already assistant professor when he went to work with Fabes. Yeah, there was no PhD. So now today we cook the Harnack inequality in a different sauce. And this time I'm talking about the Harnack inequality for parabolic equations which are in non-divergence form. And here's the plan of what I want to do. So I will state the problem and I will try and introduce the problem, particularly for those of you who might not be familiar with the theory of parabolic equations, in particular with the Harnack inequality. And then, since the result, it's not a new result because it's well known for people working in the field, then I will spend some words on the proof, and I will show how you prove it in multiple steps. First, you prove it showing an estimate from above, and then, which is the most difficult part, usually you prove an estimate from below, and then you connect them. And in particular, as far as the estimate from below is concerned, I will say a few words on some technical lemmas which are involved. And these lemmas are, I think, interesting also because they have a statement which is very closely related to analogous statements that one can have for parabolic equations in divergence form. So something that seems very far away, but as you will see, the results are very similar from different point of view. And then I will show how you conclude, and I will say just one final remark about possible developments, something that I already mentioned, by the way, when I was lecturing about the intrinsic Harnack inequality. Okay, so here's the statement. We have a parabolic equation in no divergence form. In particular, here you have a matrix A, which depends on x and t, and you have your matrix, you multiply it with the matrix of the second order derivatives, and then you take the trace of what you get. This is just a way of writing the equations in non-divergence form. And even though this is not really needed here, but we assume the right-hand side f to be a smooth function, and also the matrix to be a smooth function. So some of the operation I'm going to be will be well justified, but you can actually assume less both on f and on the matrix A. And also here, just for the sake of convenience, we assume that the matrix is bounded below by so the smallest eigenvalue is less than 1, and then again, as I said, for simplicity we assume that the largest eigenvalue is just 1, but this is completely immaterial in this kind of stuff. So you could have a larger eigenvalue which is larger than 1, this will still be okay. And in particular, just to make an example, if the matrix Aij reduces to the Kronecker delta, so it's just delta Ij, then the equation reduces to the heat equation, which is the prototype equation for describing diffusion processes. And in this case, you can think of u, for example, as the temperature, because this will tell you how the temperature changes in a body when the heat diffuses in the body itself. Just few notation because I will use them. So with BR x naught, I denote the ball of radius r, center x naught, whereas KR of x naught will be the cube, again of wedge r. And then this will be the standard cylinder. Most of the estimates will be given or proven in a cylinder. And you see that this is the cube in space. And then you have the time interval, which I always write in this way. So the cube is centered at x naught t naught, but this is the upper vertex. So I always go below. And in fact, you see the time goes from t naught minus r squared to t naught. And the fact that you have r squared here is exactly what you expect, because r squared is the scaling for parabolic equations, for linear parabolic equations. Then in one of the statements, I will also need a different kind of cylinder, which is just the cube of radius r times the interval 0t, the time interval 0t. And this is what we call the parabolic boundary of the cylinder, because if you have a cylinder, a space-time cylinder like this, then the parabolic boundary will be the lateral boundary and the lower base. So that's usually what we call the parabolic boundary. Okay, here is my statement, which is not mine, because as I said, this is a result which is well known. So if we have a non-negative solution, so u is greater than or equal to 0 of our operator, and for we take in a cylinder, this is just for the sake of convenience. You could have your result in a much wider domain, but we're just focusing on the cylinder because we're giving the estimates in the cylinder. Then there exists a constant c, which depends only on the space dimension n, and on lambda, which is the smallest angular value, which I showed you before when I first presented the matrix. So we have this constant such that the supremum over this cylinder of u is bounded above by the infimum over the other cylinder plus this extra term. Then I will say a few words about this extra term, because basically we can get rid of that, so it doesn't really matter. What is important to remark is that here you see, if you look back, if you go back to the notation I gave you before, this tells you that you have a cylinder which is centered at x naught t naught minus 2r squared, and you go below of r squared. So basically this will be t naught minus 2r squared, and you consider this guy. This is exactly what I wrote there. So this is qr of x naught t naught minus 2r squared. So here we take the supremum of u, whereas when you consider the infimum is taken over qr x naught t naught, which means that you start from t naught and you go down to t naught minus r squared, whereas here will be t naught minus 3r squared. And here you take the infimum. So as you can see, you need a gap between the cylinder where you take the supremum and the cylinder where you take the infimum. And I will say a few words about this in a second, because this looks strange when one sees it for the first time. But then if you think about the problem, if you think that u might be the temperature, this is perfectly justified. This is exactly what you would expect from a physical point of view. But for the moment, let's just keep the statement, and I'm going to write it there afterwards, right away, because I will need it afterwards. So, as I said, the Harnack inequality is the supremum over q of r x naught t naught minus 2r squared of u, which is bounded above by a constant, the infimum over qr of x naught t naught of u plus r n over n plus 1, then we take the L n plus 1 norm of f in Q of 2r x naught t naught. So this is my statement. Okay. So now, just to put things into context, let me tell you briefly a bit of the history of the Harnack inequality. So the Harnack inequality was originally stated by this guy, who was Axel von Harnack, in this book, which is the Foundations of the Theory of Logarithmic Potential and Unique Valued Potential Function in the Plane. And this book dates to 1880 something. And so what Harnack's, the statement that he gives is this one. This was originally given for n equal to 2, but actually you can write it for any number of dimension, and in fact here is written for n, for a general n, except that this is small n and this is capital N, but should be the same. And if you look at the statement, you can see that an equivalent way of stating this would be saying, exactly as it's written over there, but now we are in the plane, that the supremum of u is bounded above by the infimum of u. That's a different but equivalent way of restating the Harnack inequality. And if you look at it, of course, you need to require that this smaller ball is included in the larger ball, and they are both included in the larger reference domain. You cannot go up to the boundary because this would give you problems. And the important thing is that this estimate is scale invariant in the sense that if you fix R and you capital R, and you pick R as a constant, fixed constant, capital R, then these ratios are just numbers, and so really they don't really depend on the choice of R, provided that the ball of radius capital R is included in it. And also they do not depend on the position of the ball. So provided the ball fits into the larger reference domain, you can fit the ball wherever you want, and the statement will be the same. Okay, so this is the original statement. As I said, it was given in 2 dimensions, but you can easily extend it in larger number of dimensions. The way Harnack proved it was to write down the potential, and he relied on careful estimates of the potential. So you really need to have the potential if you want to redo the proof in Harnack style. Here's the guy, because we usually talk about the guy, we never know how he looks like. So you have a picture here. This picture has been taken from an old book that was printed in Leipzig. The interesting thing is that well, now things have changed a little bit, but up to few years ago, if you would look for an image of Harnack in the internet, you would find the image of an old guy, and that picture is surely wrong, because Harnack died when he was 37. So the old guy that you find in the internet cannot be the right Harnack. And in fact, the old guy that you would find in the internet is his twin brother, who died much later. And by the way, was not a mathematician, so it was a theologian, so he had nothing to do with mathematics. So anyway, this is the protagonist of our story. And now the question is, okay, so we have the statement for say harmonic functions. You can extend it, it's not too hard in a sense, to elliptic equation. Now the question is, what can you do for parabolic equation? What is the statement? Is it similar? So we can still say that the supremum in some ball, which in this case might be a space-time ball, is bounded above by the infimum in the same ball. And the answer is that this cannot be the statement. So it cannot be that you take space-time balls and you take the supremum and the infimum. And the example, the counter-example to this kind of statement is very easy. You can take this guy, which you can extend for t less than 0, but for t larger than 0, this is just the fundamental equation of fundamental solution of the heat equation in 2 dimensions. And you can see, just it's a matter of computations, that if you take the ball, which is centered at 1, 0, with radius 1/2, then you cannot have that the supremum is bounded above by the infimum up to a constant, because in this specific point, which is the center, this function is 0, whereas the supremum on the ball is larger than 0, so you have a contradiction. So for sure, there is no chance that you can work with space-time balls. You have to work in a different way. And then the problem is, okay, how do we write the Harnack inequality, assuming that it holds for a parabolic equation? So the answer was given, as you can see, much later, because the original statement, as I said, was 1880-something by Harnack. And for the heat equation, 2-dimensional heat equation, but again, you can write it for an arbitrary number of dimensions. But anyway, the statement for the heat equation was proven in 1954 independently. In fact, they were published in the same year, but in 2 different journals. The proofs are more or less the same. And this result is due, as I said, independently to Jacques Adamar, which is the same guy of the well-posed problems, and Bruno Pini, who's a professor at the University of Bologna. And by the way, for you, Agnid, Bruno Pini was the master thesis advisor of Nicola Garofalo, so it was not a long time ago. And I think that Nicola Garofalo was the last student that Bruno Pini had before his retirement. And as you see here, the statement is similar, and one can show that it's actually equivalent. So you take the ball of radius 2r center x naught times this time interval. So again, you have a space-time cylinder, and you put yourself at a point which is x naught t naught, and then the supremum is bounded above by this function, but you have to go below. So you have to put yourself in the ball centered at x naught, radius rho, but you have to put yourself at time t naught minus r square. So you have to be definitely below. And then, even though this is not in the statement by Adamar and Pini, you can also show that, which is equivalent, instead of writing that the supremum is bounded above by u at x naught t naught, you could rewrite it in an equivalent way, saying that u at x naught t naught bounds below the infimum taken at a later time. So instead of going here, you might go up to t naught plus rho square. Then you take again the ball of radius rho, center x naught, and then you take the infimum here, and this will be equivalent. But so the main point again is that you cannot work in balls, you have to work in cylinders, and you need to have a gap from the set where you take the infimum, set where you take the supremum, and that set where you take the infimum. So they have to, you need to have a definite gap. And this is not a surprise if you think about the physics which is behind it. And this is what I write. So assume for simplicity that f is 0, so you can throw this guy away. And suppose that at some point xt in the time interval, so in the lower part here, u is larger than 1 in some point. And remember that u is the temperature. So you put yourself in a point, and the temperature there is larger than 1. And you know very well that if the temperature is larger than 1, you have some, let me say, this is not very physical, but to give you an idea, you have some heat there, and the heat will diffuse, will spread. So if the heat spread, then the temperature around changes, and after a while, in a full cube, the temperature will be all bounded below by the constant, for example, 1/c. But in order to have this spreading from one point to a full cube, you need some time. That's why you need to have a gap, because this gap between the cylinder where you have the supremum and the cylinder where they have the infimum is exactly the waiting time that you need in order for the diffusion to be effective. And so this mathematical fact reflects a physical situation, so it's perfectly reasonable to have a situation like this. Okay, so now we go back to our result. So I want to go back to the Harnack inequality, and what I want to try and do in the following is to give a sketch of the proof of this result, because the result is well known. I mean, it's been proved in a number of different ways by different people, and I think that the way Sandro Sosa and I proved it, it might be interesting because it gives you a sort of different approach, in particular about the ways you get these estimates. And so this new approach might turn out to be useful in different contexts, so it might be extended to different situations. So let me say, the techniques in some sense are, I think, new, or rather new. The structure of the proof per se is quite classical. So first of all, we will prove estimate from above. So we will prove something like saying that the supremum of u is bounded above. Let me be imprecise, and then I will be more precise later on, by some average of u. So this is an estimate on the supremum from above. And then I will give you an estimate from below, which is usually called the weak Harnack inequality, which means in this case that the average is bounded above by the infimum of u. And then, as you can imagine, once you have these two estimates, you just connect them, because the supremum is bounded by the average is bounded by the infimum. Provided you have the right gap, you get exactly to what we want to prove. So that's the structure of what we are going to do. And as I said, the main difference with respect to known approaches is the use of the green function, which I will say in a second what exactly is. And also we will use what is usually known as the growth lemma. The growth lemma is something which is very widely used in the context of elliptic and parabolic equations in non-divergence form, but he has a perfectly equivalent statement for elliptic and parabolic equations in divergence form. The only difference is that people, for reasons which I don't know, just changed the name. So instead of calling it growth lemma, they call it the expansion of positivity lemma, but it's the same thing. And as you will see, they basically have the same statement. And I'm not going into details here, but the same kind of proof I'm going to show you can be extended to operators with bounded drift, so say first order terms, or even zero order terms. I don't want to make it too complicated, because then we would have too many terms in the way, and this would make things too complicated. This approach, so showing the estimate from above, estimate from below, and connecting them, has been introduced, for example, in the context of linear parabolic equations in divergence form by Jürgen Moser, and here's the guy. So again, because we frequently speak about mathematicians, but we never know how they look like, so the kind of face they have, so they might be like goths, but they were real persons, and this is the guy. By the way, Jürgen Moser was an extremely nice guy, and beyond being an extremely good mathematician. Okay, so let me, so again, the first point is proving the sup estimate. And as I said, I want to prove this relying on the green function. So what's the green function? Okay, we start from the problem. So we have L of u equal f in our cylinder. And then I prescribe the value. Remember, I told you the parabolic boundary, which is the lateral boundary and the lower base. And I prescribe the value to be 0. And then this theorem is due to Krylov, and it says that the sup of u in the cylinder is bounded above by the Ln+1 norm of f. This is a well-known result. I'm not going into details here. We take it for granted. What is important is that this result tells you that the green function exists. What is the green function? Well, the green function is this guy. The fact that you can write the solution as the integral of these objects times f. I recall that f is what you have on the right-hand side. So you see we have f here. And this result by Krylov tells you that you can write the solution in this way. And what is even more important is that we can have sort of precise estimate on the green function. In particular, if you integrate it to the power n+1 over n, and then you take the supremum over x and t in that cylinder, then this guy is bounded above. So you have very precise estimate, and indeed, these estimates will play a role in the proof. I'm not going too much into details because then things become a bit technical, and I don't want to stress you with a lot of computations. But in the proof of the soup estimates, these estimates on the green function will play an important role. Also, as a consequence of the previous estimate, the one that I gave you here, this one, you can actually show that you can do away with f. So you can assume f to be equal to 0. And so what I'm going to prove will be precisely, since I can do away with this because I can recover it later on, I can show you what I'm going to show is just that the supremum of u on a proper cylinder is bounded above by the infimum. So let's forget about the f. Okay? The Krylov theorem tells me that I can get rid of the f. Okay. So here's the statement. What I sketched there, now here's precise. So I take the soup of u in the cylinder, which is centered at x naught t naught with the radius r over 2. Let me make this more precise. So I pick a point which is x naught t naught, and I am considering this set. So this will be q of r over 2 x naught t naught, and then this is bounded above by a constant that depends on p, which is the same exponent that I have here, lambda, which is the smallest eigenvalue, and n, which is dimension of the space, but I have to take a larger cylinder, which is this one. So this will be the cylinder q to r x naught t naught. The important point is that these two cylinders have the same upper vertex, which is the point x naught t naught. And here the thing is that for any p larger than 0, this holds. So you can take p as large as you want, or, which is what I will actually need in the final stage of the proof, I can take p as small as I want. Because, of course, well, you will see when I state the weak Harnack what comes up. So this is my statement. So this makes precise what I sketch right there. And how do we prove it? Well, first of all, we do something, you see, I mean, this is something that a lot of people do, and I am among this lot of people. I don't really like working with R because this makes things complicated. So one thing is, okay, I can scale the variable, so I can scale space and time, so that instead of proving the original estimate with R in the way, I prove it on a cylinder which is centered in this point, which are fixed, and I just work with Q1/2 and Q2. So the R disappears, but of course, since it's scaled, once you prove it for this function, then you get back to the original one and you have the original estimate. The interesting fact is that if you make this kind of scaling, since the equation is linear, the lower bound and the upper bound will remain the same, so the structure remains basically exactly the same. So first step, as I said, rescale the function. Then second step, which is not hard to prove, but I'm not going to do it, you can show that, as a matter of fact, it's enough to prove this one. So it's enough to show that the supremum is bounded above by the 2n plus 1 norm. Because if you have this, then by interpolation, you recover the original one. So we simplify it, and we just stick to this. I want to show you that this holds. As I said, by interpolation, you can recover the full statement. So we proceed in further simplification. Okay, now we come to the actual proof. So we take a cutoff function phi, which is in C infinity 0 of the cylinder, which is 1 on a smaller cylinder. The cutoff function, this is fairly standard, is between 0 and 1. And we assume that the space derivative and the time derivative are controlled in this way. And now I rely on a very stupid thing. You know that L of u phi is equal to L of u phi. This is trivial. Now, since I know that when I have L of u equal f, u becomes the integral of g times f, then relying on this, you see that u phi is the integral of g times L of u phi because of this. And now I compute this, which I can do. It's right there. So L of u phi, remember that L is a second order operator, so when you do all the computations, you have just all the second order derivatives on u, then you have all the second order derivatives on phi, and then you have mixed terms, so you have first derivatives and first order derivatives on both u and phi. And then we know, as I said at the beginning, we recall that u is a subsolution. So by definition, since u is a subsolution, L of u is negative, or let's say is non-positive. So I can get rid of this guy because this guy has a sign. So I end up here. Now I rely on what I showed you before, so on the estimates for the derivatives of phi. And so both here and here. And so what I can show is that u phi is controlled by this. And you see, this term is exactly what I want because you already have that you have the integral of u to the power 2n plus 1, and that's exactly what I said. It's enough to show that the supremum is controlled by this kind of LP average. Whereas I have this other guy, which is not exactly doesn't look like having the right structure. But then I rely on the estimates that I gave you for the green function. So I take into account what I know about the green function, and by some computations, I get to the final result. I'm not going into details here. I know it might look not so satisfactory, but I'm trying to highlight what the main points are without getting lost in too many technicalities, because otherwise we would run out of time and also would not be too interesting. So anyway, as I said, the main point here is relying on the estimate of the green function. Okay, this is just a comment what I already said. So it's just a matter of computations, and if you are interested, I can give you the preprint where all the details are done, so you can see how this can be done. Okay, now we go to the second part of the statement. So about what is called the weak Harnack inequality, which I wrote here in a not precise way. First of all, we can assume that we have done the same kind of rescaling that I showed you before. So we are brought to working with cylinders which have size 1 and 1/2, which is simple. And also you see, whereas the first statement would be, remember, for any p. So you can take p any number. Now, the statement is there exists a p. So now this is not free, this is somehow forced. But it's okay, because this is forced, but in the other estimate I'm free to choose the p that I want, and then I will choose exactly the same p, so then I can match the two things together. And again, you see that this cylinder, here you have 1, but this is centered at x equals 0 and t equal 1, whereas, and then you go from 0, 1 below, because my cylinders always have this as the upper vertex, whereas here is centered at 0, 2, and then you go below, but this is done in such a way that the two sets remain disconnected. So again, the infimum is taken somewhere, whereas the average is taken below, and the two sets are not connected, they do not overlap, there is a time gap in between, which is exactly what I expect. Then, as I said, if you have the previous estimate, the sup estimate, which is done in this way, and then you have this estimate, so you have the weak Harnack inequality, then you put them together and you have the final result. So if I show that this holds true, then basically I'm done. I'm in business, I have exactly what I want, and there is nothing more to do. Okay, then I make one simplification, which is trivial, but it's important. Since everything is linear, you can always rescale the variable, assuming that the infimum, which I'm interested in, that this infimum here is 1. This I can do, and if I do this, then basically it turns out that it's enough to show that this integral is bounded above. Because if this is bounded above, then you take it back that the infimum is 1, and you are in business. Okay, so let me call gamma z the set in the cylinder Q101, where u is larger than z. And then this is a trivial consequence of the integration theory, that the integral over my cylinder of u to p naught can be written in this way. So you have the integral of z to the p naught minus 1, the measure of z in dz. And in particular, then this integral between 0 and 1, you can split it as the integral between, the integral between 0 and infinity, you split it as the integral between 0 and 1 plus the integral between 1 and infinity. And this is trivial, this is a number, there's no problem with this. Whereas, of course, the problem lies here. So how are we going to do that? Because my point is, if I show that this guy is also controlled from above by constant, then I have exactly what I want. So the problem lies in controlling this. But now I'm lucky enough, because I can show that my set gamma z is actually contained in the union of gamma z1, gamma z2, and gamma z3. I have to show this. So I claim that this is true. I take this for granted, that I can actually rely on the fact that gamma z is contained in the union of these sets, where gamma z1, gamma z2, and gamma z3 are these guys. So the first one was the measure of gamma z is controlled in this way. The second one is the measure of gamma z is controlled in this other way. And the third one is this, where c, capital M, rho, gamma, they only depend on lambda and n, but otherwise are completely, they basically depend only on the data. So let's assume that this is true. Then we'll get back to this. If this is true, then it's easy, because we have this integral, this term, which comes from the integral between 0 and 1, and this is the integral between 1 and infinity. And now, since gamma z is contained in the union, then this is splitted and then here you have the intersection of gamma z with gamma z1, gamma z with gamma z2, gamma z with gamma z3, and then you rely on the information that you have on gamma z1 and gamma z2, so you know that the measure decays in a proper way, which allows you to integrate. So this is a number, again, this is a number, which depends only on m, but I've said that m depends only on the data, whereas this guy here, up to gamma, remember that gamma z3 involves gamma, it's here. So if you rely on that, you end up with this guy. And now, this is fairly standard, and that's where the choice of p naught comes in. If you choose p naught sufficiently small, so that this guy is less than 1, this term can be absorbed on the other side, and you are done. So, if my previous result, my previous claim, if this claim holds true, then I'm done, provided I choose p naught sufficiently small. Okay, so this proves the weak Harnack inequality if my previous claim is correct. So the final part of my talk will be to show that my claim is indeed correct, that you can rely on this, and so you can conclude. Okay, so here are two tools which I need. So we call this first fundamental lemma. As you see, this tells you that there exists xi between 0 and 1, and c, which is larger than 0, but again, actually, c is between 0 and 1. So if you know that the measure where u is larger than z is sufficiently large, then u is all bounded below by constant times z. So if you look at it, you have a measure theoretical information because you have an information only on the measure of the set where u is larger than z, and this measure theoretical information is converted into a pointwise information. This is exactly, for the ones of you that have followed my talks about the intrinsic Harnack inequality, this is exactly the kind of statement that you have in the Giorgi lemma. Again, you have a measure theoretical information on a larger set, which is converted in a pointwise information in a smaller set. Of course, in the context of the Giorgi theory, which is useful for equation in divergence form, you rely on the energy estimate. Here, you don't have energy estimate, so you need something else. And then typically, in this case, you work by comparison, you build suitable barriers, and you eventually get to this result. Then we have another result, which is precisely the growth lemma. So here, actually, I should have written a different way, but anyway, so we know that at time 0, u is bounded below by 1 in a small ball. In the ball centered at the origin of radius epsilon r. And then what you do, you put yourself at a later time, so you go at alpha r square, so you move up, and then you have a bound below on a larger set. So again, you have an information at the initial set, which is small, and then as time grows, and here is clearly stated, it grows in a parabolic way. If the time grows, you get an information on a larger set. Of course, if the time grows, the bound below becomes smaller and smaller because, of course, that has to do with the diffusion. As time goes by, then your lower bound gets smaller and smaller. But basically, again, for the ones of you that have followed what I did in the case of the intrinsic Harnack inequality, this growth lemma is just the expansion of positivity. Okay, is phrased in a slightly different way because typically in the expansion of positivity you have a measure theoretical information at the beginning and then you expand it. Here you have a pointwise information, but the spirit is the same, that you can expand. How do you do that? Again, since these are equations in non-divergence form. There's no chance you can rely on the energy estimate. So again, you have to work by comparison. And this is very easy, provided you have the right idea, of course. So you pick this function psi, which is this strange guy. So it has this expression here, and it's 0 otherwise. And then you compute it. Here, you see there is a Q, which up to this stage is free. And you compute L of psi, and you can show, it's not too difficult to show that if you take Q large enough, then you have that L psi in Rn+1 is non-positive. So this means that psi is a sub-solution. And then if psi is a sub-solution, then U, by the maximum principle, has to be above psi. And then you choose M in the right way and also alpha in the right way, and you get the bound below. So the growth lemma, again, comes as a rather straightforward consequence of choosing the right comparison function. Once you have it, then you are basically done. Okay, now I have my two technical tools. The first lemma, which converts, I repeat, measure theoretical information into pointwise information. And then I have the growth lemma, and then I can proceed and prove my claim, which allowed me to conclude. And actually, I will only prove a part of it, because again, the second part is a bit complicated. I don't want to use too much time. I don't want to exhaust your patience. So here's the statement, the precise statement. So psi is the same quantity that we had in the first fundamental lemma. So if the measure of gamma z is bounded below by psi, then we have this relation. So the measure of gamma z decays as c over z times the infimum. But recall that we can rescale the infimum being 1. And otherwise, if the measure of gamma z is bounded above by psi, then you have either this one or the other one. Again, you see that here you have power m, so you would get the m on the other side. Or, so this is what I call gamma z2, and this is gamma z3. So this shows you that either you have the first case, or you have the second and the third. So this tells you that basically the claim that I showed you before is correct. So gamma z is indeed included in the union of gamma z1, gamma z2, and gamma z3. So what I'm going to show you is just this one, so just this piece, which is, as I hope to convince you, is a straightforward consequence of the previous two fundamental lemmas, and then I'm not going into details about the other two instances. So remember that gamma z, the measure of gamma z by assumption is larger than psi. Then you apply the first fundamental lemma, and this will tell you that the infimum of u is bound below. But if you have a bound below, now you apply the growth lemma, the second fundamental lemma, and you expand it. And the expansion will tell you exactly what you need, which is precisely what we want, which is precisely this result here. So you see, the first one is just very straightforward, very direct consequence of the two fundamental lemmas. Now will remain to prove the other part. As I said, I'm not going to talk about it. I just want to say one more word, which I already sort of hinted at during my talks. So one major problem in the theory of the P Laplacian is to show the weak Harnack inequality in a general way, in general context. And my impression is that these techniques that I've shown you in the context of linear parabolic equations, okay, non-divergence form, might be useful to solve this problem. So this is a possible hint that here might lie possible approach to this missing piece in the theory of parabolic P Laplacian. But of course, then there are some technical issues to be taken into account, because whenever you work with the P Laplacian, you have to work with so-called intrinsic scaling, which was not the case for linear parabolic equation. And so this is just a guess, a hint. And sorry, let me go. Yep, okay. So for the moment, the full implication of this approach are still fully worked out. So whenever you go climbing, this is very clear. The final top seems very close, but when you are really climbing there, you realize that the top is actually kind of far away. So you still have to go ski or climb or whatever you want to do. You still have to do a lot. So this is an encouragement to anyone who would like to try this approach. And I'm finished, so thanks for your attention. Okay, thanks.